Okay, so today we're going to be looking at a series of experiments which were done to help determine the structure of the atom. So first off, we're going to start with the cathode ray experiments, then move on to the Millikan oil drop experiment, and then finally the Rutherford scattering experiments. So first up, the cathode ray experiments. Now, you probably have heard of cathode ray tubes before, those old-fashioned CRT monitors that you may have had on your computer growing up. Those were cathode ray tube monitors, or your old-fashioned television sets. Those were cathode rays tubes as well. Nowadays, of course, we use LCDs or liquid crystal displays very commonly. But this is, what was used for the better part of a century for most displays. So how does an actual cathode ray tube work? So here's just a very rough sketch here. So there's a rough sketch of that. What we're going to need to put into here is, first off, we're going to need a cathode, because this is a cathode ray experiment. So I have right here, this is going to be my cathode, and this is going to be negatively charged. And then when we have this cathode here, we need somewhere for the electrons to go towards, and that's going to be the anode. So here's going to be my anode over here. And this is going to be positively charged. So what's going to happen is the electrons are going to be leaving my cathode, and then they're going to be accelerated towards the anode, and then they're just going to keep going on here towards the end. And over here on this end here, this is actually going to be a fluorescent screen, so we can help see the electrons. So this is a fluorescent screen. And really, it's the same kind of thing if you've seen, the old-fashioned televisions. Remember, they have those little phosphors in there, and that's basically the same stuff. When the electrons hit that, the phosphors glow, and then you can see the glowing spot in there. Additionally, there's also a little grounding plate over here, so this is just at ground. And that's just to help prevent sparks when you're doing this experiment. So basically, the electrons are going to be accelerated through here and then just keep on going. So this way you don't have any back reflections and stuff slowing these things down. So the electrons are formed over here, and this is going to be our electron beam. So you can't see the actual electrons. All you see is just a beam of electrons coming through here. And the beam of electrons will go through this, go through here, and then just keep on going until, they hit the screen. And if there's no additional electric or magnetic fields, they're just going to go in a nice straight line. And then what's going to happen is you're just going to see a glowing dot here on the fluorescent screen. You can't actually see the electrons in here because, of course, you can't see the electrons. I'm just, just drawing where the beam actually would be. Now, he did two experiments here. One was doing electric deflection, and the other one was doing magnetic deflection. So first up, for the electric deflection, he had over here basically electrical plates inside of the tube. And then this could either be positive or negative. And of course that was, connected to something outside here. And then on the other side, this would be negative or positive. So it would be, equal and opposite charges on there. And then when he applied this electrical field, well then if it was positive over here, remember electrons are attracted to positive things, well then the beam would be deflected up this way a little bit. So the beam would be deflected up that. So then you would see a dot over here, and then if you switched it around, so then the beam was negative on this side, positive over here, well then it would be deflected equal and opposite down to this point. Okay, so that's what would happen if you did, electrical deflection. So he did one, set of experiments with electrical deflection, and then he put an electromagnet on the, basically the same spot over here, and then looked for the deflection due to the magnetic field. So he would put electromagnetic here, and then this would be, north and south, or north over here and south over here. So you could, again, vary with the magnetic field here. So you'd see these deflections going on here, and then he did, a series of experiments where he would vary the current in this electromagnet to change the magnetic field until these dots lined up with the same ones as the electric field. And through there and a bunch of math, he's actually able to figure out, well, two things. One is that the electron is negatively charged. Okay, so first up, electron is negatively charged. You can find that off, very easily just from using just the electric deflection here from the charges from the plates. Now, when you do it with the magnetic field, when you combine those two things, the second thing you can find out is the mass to charge ratio. And this is the mass, of course, of the electron to charge. ratio of this. This is going to be very important, as we're going to be seeing in the Milliken oil drop experiment in a few minutes here. So we have here this mass to charge ratio, and this was determined to be 1.759 times 10 to the 11th, and that's a positive 11th, coulombs per kilogram. All right, so this is a very, very large charge in a fairly small amount of mass. Now, if the electrons weren't balanced out by the oppositely charged protons, this would be the charge in normal matter. But fortunately, electrons and protons cancel each other out exactly, so we don't have any net charge on neutral matter there. One other thing I should mention here is that this entire tube for the cathode ray stuff, this has to be very near vacuum. And the reason for that is you want your electrons to be traveling in a nice straight line. If there are gas molecules around, they will bump into them and then get deflected and then ruin your experiment. So this has to be very close to vacuum to actually work. All right, so this was done by J.J. Thomson. And this work was first published in 1897. And then he got his Nobel for this in 1906. So here we have a cathode ray tube. It's not the same one that J.J. Thomson used, but the principle is the same. So the blue glowing line is not the electrons, but is actually due to small amounts of argon present in the tube, which are glowing as the electrons pass through it and excite the argon atoms to a higher energy state. And it's really just analogous to a neon light. So here you can see the effects of a magnet on the electron beam. It deflects it downwards or upwards depending on if you have a north or south pole. Next up is something that you may have done when you were younger. You put a magnet next to the TV, and when your mom asked you to put the magnet by the TV, you blamed your little brother. So the reason that the picture gets all distorted is because the magnetic field moves the electron beam, so it strikes a different part of the screen. The amount that's deflected depends on how strong and close the magnet is. Now we can't do this with modern LCD, liquid crystal display, or plasma TVs because they don't have charged electron beams traveling through them, so they are immune to magnetic fields.
It's more like a big ball of wibbly-wobbly, timey-wimey stuff.
Alright, so today we're going to be talking about the Milliken oil drop experiment. Alright, now the reason they were doing this was to discover what the charge was on an individual electron. So here's a picture of the original apparatus that was used by Milliken back in the 1910s. But right here we'll just draw a little cross section so you get a better idea exactly how it was actually set up. Alright, so first up, I'm just going to draw basically the outside. Alright, so this right here is just the containment vessel that held everything. And on the top and bottom here, we had two plates. And this plate here was going to be positive voltage, so that's some positive voltage. Right down here, this is going to be a negative voltage. And these were, of course, basically just connected, with a whole bunch of little batteries in there. And this was on the order of about 5,000 volts or so. So it was quite a bit of voltage. And this was, of course, DC. Since we are using batteries. So it's direct current voltage, around 5,000 volts, so a pretty good amount of electricity that you actually needed there. So this was positive, that was negative. All right, and over on this side, we had where the oil actually came from. Okay, so there's a little inlet here, and this was connected to a little flask right here, and then of course this had the little bulb in it. So right here, this right here just contained the oil. So the oil would be sprayed into here, and then you would get a bunch of little oil droplets, right? So you get a bunch of little oil droplets when they actually come out of here. And this was actually termed an atomizer. So this entire thing up here was termed an atomizer. Now it's called an atomizer, but that's not completely accurate because it doesn't take the oil and make it into atoms. It's the same thing you would use on a perfume bottle. It just makes a very, very fine mist of oil droplets. And also the reason why we used oil here rather than something like water, well, water tends to evaporate, which is very bad if you plan on doing an experiment for about an hour or so. So you basically have to be watching these droplets on the order of an hour. If you used water, well, the water droplets would evaporate if it was too low humidity, and if it was too high humidity, they would start growing. So it's very difficult to control their size. Meanwhile, the oil droplets themselves tend to stay the same size, so you have minimal loss due to that, so it's actually fairly easy to actually do the experiment there. What happens is you have these little oil droplets, and there's a little hole up here, so the oil droplets can actually fall through. And basically you'll have your oil droplets falling down in here. Now, of course, you need some way to actually watch the oil droplets and add electrons to there. So first up, we have an X-ray source here. So here we have some X-rays. And the X-rays are going to come here, ionize the air itself. So they knock the electrons off the oxygen and nitrogen in the air. And then this is going to produce electrons. And then these electrons are going to go and, attach themselves to the oil droplets. Now, you may not always get just one electron, you may get 2 or 3, but you're obviously just going to have an integer number of electrons. So they can do the experiment multiple times, and then you can tease out the effect, how many electrons are actually on each oil droplet. All right, the next thing that we need to happen is obviously a little viewing port. So you need a little hole in here to actually watch all the action, right? So here's going to be your little viewing port. So this is where you're going to be watching what's actually going on. And then we'll explain exactly how we watch the whole experiment here. And then finally, you'll also need some kind of a light source because it's dark in there. So you're going to have here a little opening here where basically you have a light bulb coming in. So there's going to be the light so you can see, right? So you just need some light to actually see. And actually there was a lot of filtering going on because they needed to make sure that the light was coming through was just visible light and none of the infrared, because infrared light could go in there and actually heat the oil droplets up, heat the air up, and that could cause additional convection, which can skew your results in there. So you need to make sure that the light actually was coming in cool, so only the visible light and none of the infrared was actually making it in there. This was the gist of the experiment. So what would happen is you would have the droplets here, they would be falling under gravity, and then you would watch them in your little eyepiece here. And then once they fall enough, then you turn on the electric field. So this thing is not always on. So really I should draw here that there's a little switch actually going on with this. So there should be like a little switch that this can be on or off. So you can open or close this thing. So you can turn the voltage on or off. And you turn your voltage on or off there, then watch the droplets either rise or fall because of the electric field. Because remember, of course, electrons, negatively charged things, are going to be attracted to the positive voltage up here, and when you turn the field on, the droplets are going to start rising. You turn the field off, the droplets start falling. And you just keep doing that over and over and over again. What we need to do is explain what we're actually seeing here. We're not going to go through all of the math behind this because it can get a little bit complicated, but we can still explain this in terms of just a couple of forces. Let's start by looking at what the droplet feels. So this is going to be field off. And this, I should say, is the electric field is off. So in this case, here's my oil droplet. And I'm going to be feeling 2 forces here. One is going to be the force of gravity. And that you can't turn off because we're always going to have gravity here. Then we're also going to have an additional force working upwards, which is going to be my drag force. And this is because air has a certain viscosity. Now, we've all encountered this. If you drive in a car, you stick your hand out. As the car is going, you can definitely feel that viscosity of the air because your hand is being blown backwards. That's what we feel. Or, water has a viscosity, right? You only can go through the water at a certain speed. You can feel that drag force occurring there. So air has, that same thing. And what happens here is when the force from gravity is equal to the negative force of the drag. And the reason this is negative is because these are pointing in opposite directions here. This is what we get for terminal velocity. So if you've ever gone skydiving, you jump out of the plane, you don't keep accelerating all the way till you reach the ground. Eventually you reach, a terminal velocity as fast as you get because the drag force is going to be equal to the downward force of gravity and you cannot accelerate anymore. So when these are equal and opposite, that's when you reach terminal velocity. And from these calculations, you can actually figure out how big the droplet is, because these droplets are really, really tiny, and you can't actually just measure the size from this. So it needs to know some of the math behind with viscosity. We're not going to get into that, but that's the basic gist of what we're viewing here. Okay, so that was the electric field off. Now we're going to wash this thing, and we're going to turn the electric field on. So what's going to happen here is we're going to have our, and this is going to be the same droplet, so it's about the same size. Now gravity is still going to be pointing down, so the force of gravity is still the same. But now we're going to have the electric field being on. And remember from our orientation here, this is a negatively charged particle, so it's going to be attracted to the top portion. So that means that the force from the electric field is going to be pulling this up. So I'm going to have here the force from the electric field. And this is going to be pulling it up. What we have to be aware of here is which direction the drag force is going. Now the drag force is not going to be pointing up like it was over here, because in this case, the electric field is now accelerating this droplet upwards. So really this arrow here should be, you know, a little bit higher than what I have it. So really the electric field is pushing this thing up more than gravity's pulling it down. So it's going the opposite direction. The same thing with the drag force. The drag force is just going to be opposite your direction of motion. And that's why if you put your hand out of the car when you're going forward, you feel the wind blowing your hand back. But if you're backing up, you feel your hand being blown forward, because it's just going to be going the opposite direction that you're actually going. So the drag force here is actually going to be going this way. So we're going to have here the drag is going to be going the opposite direction because my little oil droplet is actually going up. So what we're going to be basically doing is doing a balance equation, figuring out, you know, how long it actually takes to for the little droplet here to go up, and then we're going to use this set of equations down here balancing the forces. Then we turn the electric field off, we watch the droplet fall, and then we use this set of equations here. Now we're not going to actually get into the math behind that. That's more of a physics thing, but just to explain what is actually happening here and how we can use these different forces to actually figure out you know, how fast this droplet actually goes. All right. Now as to the viewing window, how did this actually work? So we're just going to look a little bit more detail at what's actually going on in there. So inside this viewing window, you had basically a little telescope thing you're looking through. And on the top and bottom of this, you'd have two little scratch marks, just like that. And what you would be doing is sitting there with your little stopwatch in your hand, and this little droplet is going to start coming down. And you just be sitting there patiently. And then you just wait for the little droplet to start falling down. And because of the light source, it's actually going to look like a little twinkly star. So you hit this, and then what happens is once it hits this first scratch mark, and remember when it's falling down like this, the electric field is off, we just have gravity pulling it down. So it's just falling on its own volition. We start the top watch, and then we just keep watching it. And it's going to keep falling and falling and falling until it reaches this bottom scratch mark. And then you stop your stopwatch, write down the amount of time. And then what happens is, once it goes past this bottom scratch mark, you turn on the electric field. Now you're going to feel the electric field being accelerating this thing upwards. So now your little droplet, I'm just moving this over to the side so it's a little bit more visible. But now your droplet is going to start accelerating upwards, right? So your electric field, and then again, once you pass this bottom scratch mark, you start your stopwatch and you keep watching the little droplet go up, 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 up. And then once you hit that top scratch mark, you turn your stopwatch off, write down your time, and then since you've turned your electric field off at this point, now you watch your little droplet fall back down again. And you do the same thing, hits the bottom scratch mark, stop your stopwatch, write down the time, and then you go there, turn the electric field on, it goes up again, then down and up and down, and then you just keep on doing this forever and ever and ever. Eventually what he figured out, and his units were a little bit different, and the viscosity of air messed up his measurements a little bit, but you know, the current value that we have is that he figured out the charge of the electron was negative 1.6 times 10 to the minus 19th coulombs. So that's what he figured out the charge was. Actually, he reported in electrostatic units, but you know, modern convention, this would be the charge on the electron. And he figured this out, so this was published in 1913, and then he got his Nobel Prize in 1923. Okay, so this is when he actually figured that out. Now, from this experiment, remember what we figured out here was the electron charge. Okay? Now, from this electron charge, we could also figure out the mass of the electron. Because remember from the cathode ray experiments, all right, what they figured out from those experiments was the mass to charge ratio of the electron. Okay, so they knew what the mass to charge ratio of the electron was. They didn't know the mass or the charge. So now from this experiment, we know what the charge is. We take this, multiply it by the mass to charge ratio. So you just obviously just multiply this by the charge, and we figure out the mass of the electron. And that works out to be 9.1 times 10 to the minus 31 kilograms. So you could actually just figure out the charge of or the mass of the electron very easily just from this experiment without actually having to measure the actual mass of the electron. So I was able to find the original paper that Milliken wrote. Here is a diagram that he included, which is a little more accurate than my crude hand drawing and includes some of the things I left out for simplicity. Here on the left is a barometer which measured the pressure in the vessel, and this is very important because the viscosity of the air is dependent upon the pressure. Next, we notice the entire vessel is surrounded by a liquid, which is those dashed lines around G. This is 40 liters of what he called gas engine oil, and it was used as a constant temperature bath. So the viscosity of the air is also very dependent on the air temperature, so you want to keep the temperature as stable as possible by having a large thermal mass present. Additionally, temperature differences inside of the container itself can cause convection currents, which would be like blowing air on the drop, and that can cause additional forces which you couldn't easily model and compensate for. In his paper there, he said that the thermal mass bath kept the temperature fluctuations to less than 0.02 degrees Celsius. All right, so here is the air inlet which went to the atomizer that gave the fine mist of oil. That drifted down to between two plates which were held at the high voltage, and we'll see the voltage in a minute. The voltage was created by a whole stack of cells, which made a large voltage battery, and that was all controlled by a switch. The air was ionized using an X-ray source, and then those ejected electrons landed on the oil droplets and charged them up. Down here we have the light source, which passed through water and copper chloride solutions, and that was remove the heat, the infrared light from the visible light. And that also prevented the container from warming up too much. Now the viewport where he actually did wash the drops was at an angle relative to this cross section, and isn't shown here. Now in his paper he has pages and pages of data as you watch many drops, and if you want to look at those data, it's all listed down below. Here's one little portion just to give you an idea of the conditions he used. So first of all, this particular run lasted 45 minutes, and just imagine that for a minute, watching one drop going up and down and up and down and up and down for 45 minutes. So he was very dedicated in his work. Here we can see that the plates were held at a high voltage, which were set 16 millimeters apart, and the fall distance that was between the two scratch marks that I mentioned earlier on the eyepiece was 10 millimeters apart. The initial and final voltages were near 5,000 volts, and the temperature was around 23 degrees Celsius, which is around room temperature. The pressure is listed as 75.62 centimeters, and this is centimeters of mercury. All right, so 1 atmosphere is 76 centimeters of mercury, so this is pretty close to 1 atmosphere. And if you happen to watch the weather and they give the barometric pressure reading, it's around 30 inches of mercury, so that's just a simple English to metric length conversion from inches to centimeters. The density of the oil is around 0.9 grams per cubic centimeter. And here we have the air viscosity, and this is measured in a unit called centipoise. Don't worry about the unit sum, we're never going to use that in this class. Next is the radius of the oil droplet, which you used for this particular run. That varies, every run is different when you have different sized oil drops. It is listed as 0.000276 centimeters, or 2.76 microns, and that is amazingly small. And you might wonder how he was able to measure the radius that accurately. And he didn't actually measure the radius, at least directly. What he actually used was his knowledge of the terminal velocity, which is noticed from the drop actually falling, and also the viscosity of the air. And through a little math, you can actually figure out what the radius of the little droplet was. And we're not going to get into those particular calculations. Next is L over A, which is the ratio of the mean free path of air molecules, which is the L, to the radius A, which is listed above. Now the mean free path, this is the average distance an air molecule will travel between collisions. So here, if you do the calculations, that works out to about 94 nanometers. And the reason that this is important is that if the drop gets too small, then there would be additional effects that you would have to consider. But the drop is big enough relative to the mean free path of the air molecules, so we're fine there. And then we have here the speed of the fall, and this is the terminal velocity, is 0.08584 centimeters per second. So you can see that the time for the drop to fall would be about 11 seconds or so. And then finally for this run, he calculated the charge on the drop, which is 4.991 times 10 to the minus 10th. And the units are what's known as electrostatic units, not the familiar coulombs that we use today. So this works out to 1.664 times 10 to the minus 19th coulombs, which is very close to the modern value of 1.602 times 10 to the minus 19th coulombs. So it's within a few percent there. Now, not all of his runs had just one electron on the drop. So this particular one did. But some of them had 2 or 3 or 4, maybe more. But what he noticed was that all the drops, when he calculated their particular charges, were all integer multiples of the same number. Okay, now on to the Rutherford scattering.
What matters is we can communicate. We have got big problems now. They have taken the blue box, haven't they? The angels have the phone box.
Okay, so the basic things behind the scattering experiment was, first of all, get over here, some radioactive isotope which shot out alpha particles. And remember that alpha particles are the same thing as helium-4 nuclei. All right, so this is just 2 protons, 2 neutrons in a little nucleus, and this is what's being shot out of here. Okay, so these would come through, and then over here we'd have a little thin foil of gold. Okay, so this is gold. And this is very, very thin. It's on the order of, around 1,000 atoms or so. So this is a very thin foil of gold. And the reason we use gold here is if you've ever done anything with gold leaf, you may be familiar with that. You can take gold and pound it very, very thin. Also, what is very useful is that unlike many other metals, gold does not oxidize with oxygen in the air. So you can have the gold being very thin and not having to risk it reacting with anything else, and it will still just remain gold. It's not going to become gold oxide or anything like that. Because it's low reactivity and it can be pounded very thin, that's why we used gold for this particular experiment. All right, and then surrounding this was a fluorescent screen. So this is a fluorescent screen, and this is made of zinc sulfide. So what would happen is when the alpha particle will strike the zinc sulfide, a little flash of light will be given off, and then you can make a little mark, where that alpha particle actually hit. So this was the way that they could detect the alpha particles in those days. So we would have our alpha particles here, coming through, and there would be a couple of collimators there just to make sure that, the alpha particles were traveling in a nice little line. So you'd have basically just some nice little collimators. Just to make sure that the alpha particles are going in a straight line. So you have the alpha particles coming through here, and then they're going to impact the gold foil. Now we're going to examine in detail what was the expected and the actually observed results and why this was actually happening. So the alpha particles impact the gold. Now most of them just keep on doing their own thing, keep going on in a straight line, deflected very, very minimally. So this is the vast majority. Just go in a nice straight line, and it's like nothing really happened. And that's also why we want a very thin foil, because of course if you get something very thick, well, the odds of actually hitting something go up dramatically. So you want something that's very thin there. All right, and then of course a couple of them, wind up, being deflected a little bit. But what really was the very shocking ones was occasionally you'd get, an alpha particle which would come off here or down here or something, and the ones that would be deflected just dramatically, this happened about 1 out of 8,000 times. So it kind of gives you an idea how many times they actually had to count these and how many little flashes they had to record to notice a 1 in 8,000 deviation. So it's a very small amount that actually were deflected by this amount here. And from this, Rutherford was able to figure out that, first of all, how the gold nucleus or how the gold atom was actually put together is that it wasn't just a continuous distribution of charge, but it actually has a heavy, dense nucleus. So that was his big discovery here, is that the nucleus is heavy and dense. So as for a little history and why he actually went to do this experiment here, was trying to figure out what was actually going on in the atom. Now, first of all, the theory was initially, called a plum pudding model of how the atom was actually put together. So the idea was you'd have here's your atom, a nice little sphere, and inside of this atom you'd have your little plus charges all around there, you know, just evenly distributed, and then you would have an equal number of negative charges inside of there. Okay, so this was what was called the plum pudding model. Now you have to realize that when Rutherford was doing this, Rutherford is from England, so their version of pudding is not the same version of pudding that we're used to. Okay, so really if he was, you know, nowadays we might call this the raisin bread model, okay, because it would probably be more accurate. The plum pudding, of course, it's kind of like our raisin bread, of course, using plums, of course, but the thing is here, all these little electrons would be the plums distributed in the pudding. So, or like we would say over here, the raisins distributed in the bread. So you have all these little negative charges, and of course if you want to ionize an atom, remove one of the electrons, you just kick out one of these electrons here and you get, you know, leaving behind the slightly positively charged atom over here, or ion. So that was the plum pudding model. Now if this was valid, if he was doing this experiment, the stuff would all be basically just kind of deflected, you know, in a little range over here. You really wouldn't get anything being deflected at these very large angles, because you would basically have an even continuous charge distribution, so you wouldn't notice like any large discontinuities that we're actually seeing. So instead, what Rutherford actually saw was basically a bunch of little plus charges all concentrated in a very, very small location, and then a bunch of negative charge all around, you know, in the very, very diffuse area here. Okay, so when he had this is, you know, of course, the Rutherford model of the atom. We'll look in more detail how the atom is actually put together later on. But essentially we have here this cloud of electrons around the outside and a very dense nucleus here on the inside. And actually this is not really to scale. The positive charge is very, very small. So just to give you an idea of the size of this, the entire size of the atom here is about 10 to the minus 10 meters. The nucleus itself is around 10 to the minus 15 meters. Okay, so this is 100,000, yeah, so this is 100,000 times smaller than the atom itself. And that means that the volume of the atom relative to the volume of the nucleus is on the order of 10 to the 15th times difference. So saying that the atom is, you know, the mass is concentrated in a very small location is quite an understatement. The mass is concentrated in a very, very small volume of the atom. The atom's volume itself is mostly empty space. Now, of course, what do we mean by empty space? Well, that gets into a whole can of worms we don't really want to enter into, but the nucleus itself composes a very, very small volume compared to the entire volume of the atom here. All right, now as for, you know, how the scattering actually results in what we observe up here. So remember we have these little scattering, and I'll just redraw the atom over here. So essentially what I have here is a positively charged nucleus, and then I have all my little negatively charged electrons around the outside here. Okay, so that's my electrons. There's my atom. What's happening here is if you have these alpha particles coming in, so here are my alpha particles over here. Basically, these are a beam of electrons. So even though these are coming in, we've collimated, they're still a little spread. They're not going to be, you know, isolated just down to the accuracy of an actual nucleus. So there's going to be a little bit of spread here. So you're going to have a bunch of alpha particles coming in, you know, at slightly different positions. And if you're far away from the nucleus, they pass by and really don't notice anything, because the nucleus is far away, so they just go on their merry way and don't interact, and then they just appear on the other side and impact the screen. So if they're far away from the nucleus, they just come right here. But as we start getting closer to the nucleus, well, what we're going to start noticing is these start getting deflected a little bit. You know, so these get close to the nucleus here, and they get repelled, because remember, the alpha particle is a positively charged ion. The nucleus is positively charged. So if you get close to that positively charged nucleus, and that shouldn't have curled up so much, but you start getting these deflections. And if you get closer to the nucleus, this is what we see, these occasional deflections which come off, and that's why occasionally, you know, we see, you know, something along this line. So these are the ones which are close to the nucleus but not actually impacting it. And then occasionally what happens is you get something that comes basically straight on. So you have this one coming in here, it sees the nucleus and slows down and then does a 180, and basically turns around. And this is what we're seeing for these nuclei. Now, of course, the ones that are exactly 180 degrees change, we don't actually see because the screen doesn't go there. But if you get like just really, really close, but just a little bit off center, then you get these very large deflections, which occurred about 1 out of 8,000 times. And a few years later, when Rutherford was reflecting upon his experiments, he said, and I quote, "It was quite the most incredible event that had ever happened to me in my life. It was almost as incredible as if you fired a 15-inch shell at a piece of tissue paper and it came back and hit you. On consideration, I realized the scattering backward must be the result of a single collision, and when I made calculations, I saw it was impossible to get anything of that order of magnitude unless you took a system in which the greater part of the mass of the atom was concentrated in a minute nucleus. It was then that I had the idea of an atom with a minute massive center carrying charge." All right, and then basically that was how we figured out the nucleus. Now, after he was doing this, he also hypothesized that there might actually be neutrons as well, because he started looking at the charge on different elements and started noticing that the mass of the element did not correlate perfectly with the charge, that there seems to be an extra little mass left over. So he started hypothesizing maybe there is actually a new particle known as the neutron. And he hypothesized that a few years after these experiments, and then about 10 years later, Chadwick actually figured out that the neutron was a particle that was unique in itself. Now, this is a sketch from a paper from Geiger and Marsden. This is the same Geiger from the very famous Geiger counters, which you're all familiar with, that help detect radiation. Well, anyway, Rutherford used an apparatus similar to this. So R is where the radioactive alpha source was located. F is where the gold foil was. S is where the fluorescent zinc sulfide was located, and M was a microscope which could watch for the flashes of light. Also, this apparatus was under vacuum, which was sucked out through tube T down here, because the alpha particles are easily scattered by air molecules as well. So you want not to have vacuum so there's no additional interferences in there. Additionally, the microscope and screen rotate around the foil. So that's B, which can rotate around there. So this way you can look at the number of alpha particles at different angles. So really he wasn't trying to measure all the flashes at different angles simultaneously. Instead, he was measuring the rate at which the alpha particles have from different angles there. So here we have the data from Geiger and Marsden. Now they also looked at silver as well as gold. In the first column we have the angle of deflection. 0 would be directly in front of the beam, 180 would be behind the beam. In the second column we have this 1 over sine of phi over 2 raised to the 4th power. So when you do the math, it turns out the scattering equation depends on the angle in this way. Now you can easily get those figures by taking the angle in column 1, dividing by 2, taking the sine, raising it to the 4th power, and then taking the inverse. So this is just good calculator practice if you want to look at that. In columns 3 and 5 we have the actual data that they collected for the silver and the gold. And in columns 4 and 6 we have the data divided by the angular correction factor. Although as I look at it, I think they have a typo in the paper. That should be n times the sine to the 4th factor, not divided by. It might just be an older convention. But in any case, those values are approximately constant. And the deviations they have are systematic, so this could be caused by asymmetries in the apparatus and higher order effects when dealing with larger values. But remember that this was the first experiment that was done, so techniques and data improved over the next few decades. And in this one here, I just plotted the data that we just saw. It's on a log scale, so we can see all the values, and this has the gold in red and the silver in blue. Now, experiments like these continue to this day. If we want to determine the structure of molecules like proteins, X-ray scattering is used quite often. Also, when they were looking to see if protons and neutrons had some structure inside of them, they scattered electrons off of the nuclei and determined that yes, there actually must be quarks that exist inside of there. And also from this, you determine that the quarks have charges not of +1 or -1 times that of the electron, but actually 2/3 or 1/3 of the electron. And this was figured out through scattering. And as far as we know, the electron doesn't have any internal structure, at least down to 10 to the -18th meters. And again, this is determined from scattering experiments. So really, the scattering work that was done by Rutherford wasn't just to determine, that the nuclei exists, but is also how we are able to determine the structure of matter at molecular and subatomic scales to this day.
And that's it, I'm afraid. There's no more from you on the transcript. That's the last I've got. I don't know what stopped you talking, but I can guess. They're coming. The angels are coming for you. But listen, your life could depend on this. Don't blink. Don't even blink. Blink and you're dead. They are fast, faster than you could believe. Don't turn your back. Don't look away, and don't blink. Good luck.